All right. So we did these problems before you left the other day, right? Yes, we did. Come on. There we go. And the reason why we stopped with this next one was because 20 was not perfectly within, right? Exactly. So you use the standard deviation of the mean. Can you remind me, please, because it's on the previous page. What was the mean? 24 and the standard deviation of 5?
Yes.
So you subtract 1 and you get, I don't know why I'm putting a negative because of minus 1, I guess. Yeah, 19. Then you add 5, 29. And so with the empirical rule, from here to here is 68% of the data, right? And yes, you can split that and have 34 and 34. And then you can do it again and again and again. That's what we did the other day on the previous slide. So now, though, what happens when you have 20? Well, 20 is right there. So if you want to find the probability that's less than 20, you can't use the empirical rule, right? So what do? What did we do the other day when we have values that didn't fall perfectly using that standard deviation and that mean? Z-score. Very nice. So Z sub 20, which is the score I'm looking for. And then tell me, how do you find the Z-score? It's your value minus your mean divided by standard deviation. Nice. So that would be negative 4/5, which is negative 8/10. And that's where the chart that I just gave you comes into play, that orange chart. Okay. So if you look at your chart, you have a column down the side, right, with negatives. Let me get this going. Sorry about that. You have those negatives. So if you look, it starts with negative 3.4. Everyone agree? Are you with me? And if you look across the top, it says 0.00, 0.01, 0.02, all the way up to 0.09. Well, so let's say my Z-score is negative 3.46. That means I would go up here to the negative 3.4 and then over to where I see the 0.06, because the 4 takes that tens place of 0. You see what I'm saying? So my Z-score is negative 3.46, so then my probability is 0.0003. Because look, this is your Z-score, and the probability is the area to the left of it. All right? So because the mean is in the middle, see what I'm showing you? The mean's in the middle, right? These Z-scores are all negative, which means they're less than the mean, right? Well, the mean represents how much of the data? 0 Z-score, okay, and how much? 50%. It's in the middle. The mean's in the middle. So all of these values, if you notice, are less than 50. Because if you look, 0.09, if you go across, is 0.4641, but look at 0.00. It's 50. Because it's half. So if you have Z-scores above the mean, clearly it's going to be more than 50, right? So you flip yours over, look at the back, here's your positives, okay? Everybody understand how to read this? So go to your tenths place and then go over to whatever the hundredths place is, all right? So let's look for what number? What was our Z? Negative 0.80. So go down to negative 0.8, over to 0 in the hundredths place. So my probability is 0.2119. Yep. Well, are we looking for percents or probabilities? Probabilities, so you would just keep it. If you're looking for percentages, you would move the decimal twice. Yes. Probability is between 0 and 1, because if it's a 0, it's impossible. It's never going to happen. If it's a 1, it means it's 100% likely. Like it's certain to occur. So probabilities are always between 0 and 1, because you're saying out of 7 people, 1 of you play basketball. Let's say that's my probability. Well, 1/7, and you just, whatever that decimal is. Okay. All right, sorry. Let me get that back going. So what was my probability so I can write it? Oh man, my computer's freaking out where we switch from the document camera. All of you good on reading that chart? That way I don't have to switch again. So how do you write that? P of Z less than, and it's your Z score, not your raw score. So not 20, but negative 0.8. This means probability. Probability of Z less than negative 0.8. And it was 0.2119. Is that right? Okay. Notice that chart always shades to the left. Look at your picture. It always shades to the left. So how then can we figure out greater than? Do what? Look though, which way is it shading? Even though, yeah, it's shading to the left on the back as well. How about figure out your Z for this, and then we'll talk about it, okay? All right. This one, what'd you get for the Z score? 2.2. Okay. So if you look at that on your Z chart, first of all, time out, let me back up. Just because you learn Z scores and probabilities with Z scores, don't just automatically think now every problem is going to be a Z score and use that chart. If it's the empirical rule, use the empirical rule. It's way faster. 68, 95, 99. Okay? But if it doesn't fall perfectly on your number line when you make using your standard deviations, you know what I'm saying? Then convert to the Z score and use that chart. Okay, so sorry about that. If you look on your chart, it gives you the probability that Z is less than 2.2, right? So what did you get? And let me double check. 2.2? 2.2, we're on the back. 0.9861. So let me show you what you're saying. You're saying Z is 2.2, which is above the mean, and the probability that it's less than that, all of this, is 0.9861. Ah, what if we subtract from 1? Because what did I say a while ago about probabilities? They're either between 0 and 1. So under your curve is 100% of the data, right? Well, 100% as a probability is 1. So if we want greater than 35, yes, we have to subtract. So the probability that Z is greater than 2.2 is 1 minus 0.9861. And what did you get? I saw you had already done it. What did you get? 0.0139. Nicely done. Did you remember that from Algebra 2, or you just used deductive reasoning to figure that out? Good, nice. Okay, any questions on that? Do you see this notation? So from now on, if I ever use that notation, I expect you to know what it means, okay? P of this means the probability of this happening, all right? How are we going to figure out between 22 and 30? Subtract what? Nice. The Z-scores? Subtract the Z-scores? Find the Z-scores. Does 22 fall perfectly on it? Man, I cannot draw a straight line ever. It's terrible. Okay, so if this is my median, my middle, my mean, that's 24, right? And then minus 5 was 19, plus 5 was 29. And then I could keep doing that, so 14, 34. Clearly, I'm asking from 22, which would be somewhere right in here, right? 22 to 30, which would be here. So how can I find the probability between those two? Find the probability of them both and subtract. I'm impressed with how quick y'all are saying that stuff. Does it just make sense to your mind? Yeah, because that's okay. I'm going to show you, so don't worry. If you find this Z-score, Z sub 22, that would be 22 minus 24 over 5, which would be negative 2/5, which is negative 4/10, right? So look on your Z chart. What's the probability that it's less than negative 0.4. Good. So the probability that Z is less than negative 0.4 is you're exactly right, 0.3446. Okay? So now, let's find the Z-score for 30. So 30 minus 24 divided by 5, which is 6/5, or 1 1/5, right? Which is 1.2. So now I flip my Z-table over. This is called a Z-table, by the way. It's all your probabilities for your Z-scores, all right? And this is why I round Z-scores to the hundredths, because of this chart right here. So 1.2, 0.8849. Very good. So the probability that Z is less than 1.2 is 0.8849. Yeah. All right, so let me show you, because you're visual, I'm pretty sure. I remember that, right? Aren't you visual? Yeah. So what you're saying is when you convert to a Z-score, it makes the mean become what number? 0. So you're saying here's the mean of 0, and you have negative 1 down here. Well, then negative 4/10 would be somewhere about right there. So you're saying the probability of this is 0.3446. That makes sense? Okay. And now you're saying the probability of 1.2, so I have to go up 1, then 2 standard deviations. So 1.2 would be about right here, right? You're saying all of this, all of that is, so you can subtract the two to figure out in between. Yeah. So literally to find the probability, and the way you write that, the probability that Z, nope, the probability that it's between, so negative 0.4 is less than Z is less than 1.2. You have to put it between, right, because it's in between those two, is equal to 0.8849 minus 0.3446. So 9 minus 6 is 3, 4 minus 4 is 0, 4, 5. So the probability is 0.5403. I always write the 0 in the front. Someone asked me yesterday, so let me tell you why. A couple years ago, my seniors in statistics had a group project, which, yes, you do group projects in here sometimes. And one of the students sent her data and did not put the 0 in front. So her two teammates had to calculate the standard deviation and variance and everything, right? So all three of them calculated, used all three of their data together, and two of them got totally different numbers from her. So once they started figuring out what had happened, it was because her teammates didn't see the decimal with her handwriting. They didn't see, because she wrote it kind of just like that, like super tiny, you know what I'm saying? And they were just trying to get it done because y'all have so much work. So because of that, you know, if that 0 had been there, people don't write 021 for 21. So if the 0 had been there, it would have clued them in that, hey, there should have been a decimal. So I just started from then on always putting the 0 to try to model like, hey, this is what you should do. So anywho, I will not count points off if you don't put the 0, but your decimal better be obvious if you don't, okay? All right, go ahead, size of Texas, yeah. Go ahead and do this one and then compare with your friend. I'm not going to work this whole thing, but just let me know, what'd you get for the Z-score for 32? 1.6, everybody? Yep. So then the probability that Z is less than 1.6? I'm
0.9452.
Thank you. Okay, and then the Z-score for 35?
2.2.
We already did that one, didn't we?
Yep.
So then the probability that Z is less than 2.2 was 0.98. I put the point in the wrong place. Let me put a 0 because I just told y'all I said that 0.9861. So then the probability between Yes, you subtract. So between 1.6 and 2.2. You okay over there? Yeah? Oh. 9, 4, 5, 2. What'd you get when you subtract? 0, 4, 0, 9. You second that? Everybody good? You third? Yay! Look, everybody's agreeing. Okay, so what happens, though, if you have a distribution that is not normal, right? Haven't we worked with data where it's not normal? So time out, don't freak out. I'm going to make this bigger because apparently on your notes, it's tiny. I'm sorry. I apologize about that. You could read it, you just couldn't see the chart. Is that better? So time out, let me back it up. Chebyshev's theorem is for any distribution. So I said the other day, the empirical rule, you can use it to like guesstimate for other distributions, but it's really only accurate for a normal distribution, right? And did I tell this class? Sometimes it's hard where I have you all on different days. I did tell you all, if your mean is approximately the same as your median and your mode, then it's normal. Didn't we talk about it? They don't have to be the exact same number to be normal. If they are the exact same number, it's perfectly normal, right? But that rarely happens in real data. So the distribution, as long as it's clustered in the middle, like the majority's in the middle, and it's less on the ends, the tails, then you say it's approximately normal, okay? It does not have to be perfect, though. That really doesn't really happen in the real world, okay? It's just approximately normal. So Chebyshev's theorem tells us that the proportion of any distribution that lies within k standard deviations of the mean is at least 1 minus 1 over k squared. You need to memorize that. 1 minus 1 over k squared. Where k is any positive number greater than 1. This theorem applies to all distributions. That's what makes Chebyshev's theorem so amazing. You can use it with bimodal. You can use it with skewed. Okay? Chebyshev's a genius. Yes, I agree. So, why does k have to be greater than 1, though?
It's 1 over.
Yeah, look. 1 minus 1 over. If k is 1, then that would be 1 squared, right? But that's equal to 1 minus 1, which is? Does it make any sense to say 0% of the data is within 1 standard deviation? That makes no sense, right? So do you understand how to use Chebyshev's theorem? Possibly? Well, let's see. Before I do this example, I'm going to make a new page. Do y'all have some space in the margin? Yeah, cool. You have plenty of space. Good. I made a mistake of just assuming that people would go, oh, yeah, I get that, and not actually showing them. So let's walk through just a couple values for Chebyshev's theorem. So if I said for this right-skewed distribution, how much of the data is within 2 standard deviations? I don't know why I put a period after the 2. Should have been here. So how do I figure out how much of the data, at least how much of the data? What would I do? 1 minus 1 over however many standard deviations, so 2 squared. So 1 minus 1/4, which is 3/4, which is 0.75. So how much of the data? 75%. And notice it says at least 75%. It could be more than that, but we're saying at least 75% is going to be within 2 standard deviations for any distribution, okay? So what if I said 1.5 standard deviations? Can you do that one? It says as long as k is any positive number greater than 1. So can I use 1.5 standard deviations? Yeah, so it would be 1 minus 1 over. I like to use 1.5 as 3 halves because I can square that. So that would be 1 minus 1 over 9/4. So I flip that, which would be 1 minus 4/9, which is 5/9. So it's about what? No, 0.555, right? Okay, so there was a student I taught 3 years ago, and he was on the math team at Bassett. And I had never paid attention. 1/9 is literally just 0.11111 forever. 2/9 is just 0.2222. 3/9. 3/9 reduces to 1/3, which we all know 1/3 is 0.33333 forever. 4/9 is, yeah, so all the ninths, I can do them really quickly now because of him. It was really amazing. I love to learn stuff from you all. And because one day I said the same thing. I said, how did you just do that quickly? You know, and he was like, oh, the ninths. They're just whatever the numerator is, repeating. I was like, does it hurt? Having a brain, being that smart, does it hurt? Okay, so 5/9 in, 5, and I rounded the 5 to a 6, so it's about 56%. So let's do one more, because the empirical rule is 68, 95, 99, right? You can't do 1. You can't compare 1 because I just showed you that would be 0. So we can compare 2. So 95 for empirical rule. This one for 2 is at least 75. So let's look at 3. 3 standard deviations. Be 1 minus 1 over 3 squared, which is 1 minus 1/9, which is 8/9. So you tell me, what would that be? 0.88888 repeating. So I round that to, I know, look at her go. He was a genius. It was really fun to teach him. He taught me some really cool things. Helped you in math class because of things like that he learned on math team? Yeah. So at least 89%. At least. It could be more than that, but it's going to be at least 89% of the data. So do you see the relationship between Chebyshev's and the empirical rule? Think about those two things. The empirical rule is for a normal distribution. Well, yeah, the majority is going to be from here to here and from here to here, right? I mean, that makes sense. But think about if you have a skewed graph, right? That's skewed to the right. So our mean is probably going to be somewhere over here, right? But then we're saying within 1 standard deviation of the mean, we can't talk about 1, so we have to talk about 2. And 2 standard deviations of the mean is at least 75% of the data, which that makes sense because look how long that tail is, right? So Chebyshev's theorem is amazing, super powerful, okay? So the results of the physical fitness strength test given to some 3rd graders are given below. Their test results are listed in rank order and are shown in the histogram. So here's the rank order, put them in order for you. And here's the histogram of strength. I think literally they only named it Histogram of Strength because it's a stats book. If y'all ever call something a histogram of something, I will say, no, don't do that. Just call it strength or fitness test of strength or something. You know what I mean? Don't say it's a histogram of it. No. Strength of the histogram. No. Okay. So clearly this is not normal, right? It's not normal. It's not skewed. I would almost call it bimodal, but it's not. Bimodal means 2 modes. So it has 3, doesn't it? Trimodal. If one of you wrote that, I probably wouldn't count it wrong. But I would just talk about the distribution, how it's not skewed, it's not normal. There's more values in the class that has a mid-mark of 5 and 15 and 20. You know what I mean? Like, I would just talk about it that way because it's definitely not bimodal. There's 3 of them. All right. So if you look at this, okay, it is not normal. But you all are getting ready to get a project where you're going to have to collect your own data, and then you have to figure out if it's normal so you can use empirical rule, or is it skewed somehow and you have to use Chebyshev's theorem. Well, how is one way to determine if it's normal without making a histogram? Without making a histogram. So if you have raw data, and I don't let you make a graphical display, you're going to look at the what? The mean. What else? Median. And mode. If they're about the same number, then you can use the empirical rule. But I'm going to make you take it a step further. I'm going to say verify. Because what if you had a mistake, right? You don't make mistakes? Yeah, okay. So I'm going to show you using this example how you can verify it without using these and without looking at the chart. I'm going to make you have a three-way show me. So you 3 ways, right? The first way, you're going to compare the mean, median, mode. The second way, you're going to look at the graph. So you're going to say it appears to be skewed left or skewed right or normal or bimodal, okay? And the third way, you're going to actually look at the raw data, and I'll show you with an example in just a second, okay? All right, so if you look, we're going to use this data to determine the mean and standard deviation. Some of you told me the other day you already forgot how to do that. So go ahead right now, tell me x bar, and I'll give you a hint. The formula for the standard deviation S is the square root of the sum of the x squareds minus the sum of the x's, and you square that number. Then you divide by n, then you divide by n minus 1. I was trying to say 9. It's n. Okay, so remember, you can use your calculator to get your sum of your x squared, right? And to get your sum of your x's, remember? I know y'all are all thinking, well, we can actually use the calculator to find s. I know you know, but you don't get to do that till second semester, so. No, it's.
The first one you don't square, the second one you square.
Time out. You got the same number for your x squared and your sum of your x's? No, it's not the same number. The sum of the x squared means you literally square every value and then add it together. Yes, I'm serious. That's what this means. Remember the table y'all had to do? And you had the x's and you found the sum. Then I made you square all the x's and find the sum. Yeah. Okay, this last one, you literally just take all these x's, add them up, and then square that number. So your calculator, if you type it in L1, right, then you go to stats, arrow over to calculate, one variable statistics. What does it give you for your sum of your x squareds?
I got 2, 4, 6, 7,
2, 4, 7, 6, 4, 2.
2, 4, 6. Just switch your
6 and 7.
Yeah. For what? That's what I
For
got
your sum of your x squareds.
Yeah. I got 13,000. Am I looking? I'm looking at the wrong thing.
I don't know if you're looking at the wrong thing.
Let me bring it up to you.
That's okay. 13,500. 572. Thank you. Woo! I'm a little nervous because y'all aren't confirming, so let me look at your calculator.
Is that the sum of x, but it doesn't have a square on it, or what? No, the sum of x squared.
The sum of x, yeah, he has 2, 4, 6, 7, 4, 2. He's right.
I kind of like
Typed them in really quick. I watched you.
Yeah.
You weren't looking at your calculator very much. You were just.
So,
yeah. Okay.
So who's right?
I don't know. Let's see.
There's a lot of.
So the sum of x's, what'd you get for that piece? 832. What did you get? What'd you get for this one, though? You didn't type them all in? So you didn't get your sum of x's squared? N is what? How many data values?
832. I got 816. You missed the 16.
And then what happens when you square root?
You get a number.
You get a number. Really, y'all? You get 6.614? When you use these values, that's what you got. Right. But did you use those values, or did you just type in your calculator? Okay. You all are really going to have to do this on the test that's coming up. That's okay. I believe you. If you're lying to me, it's just going to hurt you, not me. You know what I mean? I've passed stats, so I'm the one grading your test, and I'm telling you, you're going to actually have to do this. Okay? What was your mean?
Oh, yeah. I didn't get it.
The mean is 13. Yeah, and this is 6.614078299. Yeah. So you're right. You can round this. So is this distribution approximately normal? Let me show you how, though. Remember I said I was going to show you the third way to verify? So look, if you go to the middle, that would be 13, right? And then let's just round this to 6.6, right? Our standard deviation. We're allowed to do that. So 13 minus 6.6 is what? 6.4. Then if you add 6.6, 19.6. Yeah? So if it is normal, how much of the data should be from here to here? 68%. Right? So let's look. Numbers between 6.4 and 19.6, right? Where's the first number between 6.4? So here, all the way up to 19.6. So here. So how many numbers is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 32, 33, 34, 35, 36. So 36 divided by how many do we have? 64. And you get what? It's not. What do you get? You get what? 56%. So do you see how to verify that it's not normal? So 1, compare the mean, median, and mode. 2, make a histogram. Look at it, right? 3, actually use your mean and standard deviation to determine if it's normal or not. Because if it's not normal, we have to use which rule? Chebyshev, right? So Chebyshev says that how much of the data should be within 2? 75%. At least. It could be more than that. But you know what I'm saying? At least 75%. So 2 standard deviations would be how much?
Well, 13.8.
So I would subtract 6.6. That would be negative 0.2, right? And add it to this one. 19.6 plus 6.6 would be 26.2. Yeah, sure. That makes me nervous.
No, not like that's for sure. Like I messed up.
Is that right? 26.2? Okay. You're going to make me actually have to write it, aren't you?
No, that's right. It should be. That's right.
Okay. I feel better now. All right. So how much of the data is between negative 0.2 and 26.2? Well, let's look. All of it, 100%.
Whoa.
Is that at least 75?
Yep.
Yeah, so Chebyshev's is right. Okay.
Yeah,
Chebyshev's uses a conservative approximation. Because look, this is still pretty clustered in the middle, isn't it? It's not like I have bars up here really high and then they get smaller, smaller, smaller. So it's not really skewed. It's still pretty clustered in the middle. It's just definitely not normal, right? All right, let's answer the last question. So the scores achieved by students in America make the news often, and all kinds of conclusions are drawn based on these scores. The ACT assessment is designed to assess high school students' general educational development and their ability to complete college-level work. One of the categories tested is science reasoning. Hey, y'all, this is ACT. Some of y'all take this. Okay. So the mean ACT test score for all high school graduates in 2008 in science reasoning was 20.8 with a standard deviation of 4.6. According to Chebyshev's theorem, at least 89% of high school graduates' ACT scores in science reasoning will be between what values? Well, remember, 89% was how many standard deviations away? 3. Good. Did y'all write this down?
Yes.
Good. So 3 standard deviations. So what does that mean? It means we'll take the mean, so 20.8, and it's plus or minus, right? 3 times what? 4.6, because it's 3 standard deviations. See what I'm saying? So 20.8 plus or minus what? What's 3 times 4.6? Thank you. 13.8? Do y'all agree with him? He did, because 3 times 6 is 18, so you'd carry that 1, right? And then 4 times 3 is 12. 12 plus 1 is 13, and then 0.8. Didn't you do it in your head? Did you type it in? Oh. That's okay. I was doing it in my head. That's okay, though. That's okay. All right, so 20.8 minus 13.8 is 7. So they're going to score between 7 and
34.6.
34.
Oh, wow. I was gonna make that way more hard.
I love storing for X.
Yeah, don't make it more complicated than it is. Here's the deal, though. Empirical rule, I remember because we use so much. 68, 95, 99. Chebyshev's not as much. So because I know that formula, though, I can find any standard deviations away from the mean. Because Chebyshev's, as long as it's bigger than 1, you can find how much of the data is 1.8 away from the mean, you know, because you just plug that in for K. All right, if we know the ACT scores are normally distributed, what number should you be saying in your head right now for normally? 68, 95, and then 99. So what percent of ACT scores are between 11.6 and 30? Well, first of all, are those numbers perfect, or do you have to convert them to z-scores?
Yeah, you have to add 0.8.
So let's look. What's the mean?
20.8.
20.8? Is he right?
Yeah.
Good. It's not that I doubt you. I just want to make sure everybody. Okay, so then you subtract what?
Subtract
4.6. So if you subtract 4.6, you get 16.2. And if you subtract 4.6 again?
11.6.
11.6. Okay. And then 20.8 plus 4.6.
25.4.
25.4. If you do it one more time?
30.
30. So look, it's asking me how much of the data is between here and here. 95. You're done. If it didn't work out perfectly, find the z-score, find the probabilities, and then just subtract. Okay? All right, you do have a worksheet, and you do have 15 minutes of class to work on it. So yay. Yes, we'll listen to music. Hey, folks, on Tuesday, we're going to go over this worksheet, review some stuff, and then you'll have a quiz on Thursday, or wrong class, Wednesday. Calc test, I know. I'm debating on, here's the problem, though. If I don't give you the quiz on Wednesday, then it pushes it to the next week. Because you don't have me next Friday.
We don't? I thought we were gonna have...
No, today you had Monday, Wednesday, Friday last week, Monday, Wednesday, Friday today. So next week's the Tuesday, Thursday.